All right, we're on stand number 2 here with this particular principle, the guiding principles of scientific inquiry number 2, linking to relevant theory. Here we go, number 2 of the series. So this is the two-parter. This is the second principle, third part of the series. So we had an introduction. We covered principle 1 the last time. Principle number 2 here is linking research to relevant theory. In that significant questions thing is very much related to this. And when you're asking your question, that's one of the next things to do with the guiding principles here of scientific inquiry is making sure you're linking to something that is relevant in theory. So let's read a little bit. This is actually a shorter section than it looks. So we'll read a little bit through here and I'll give some commentary to hopefully illuminate some of the language. Scientific theories are, in essence, conceptual models that explain some phenomena. They are, quote, nets cast to catch what we call the world. We endeavor to make mesh ever finer and finer. Indeed, much of science is fundamentally concerned with developing and testing theories, hypotheses, models, conjectures, or conceptual frameworks that can explain aspects of the physical and social world. Examples of well-known scientific theories include evolution, quantum theory, and the theory of relativity. So that's the general thing. It is one of the basic things of science is that we are concerned as a method of finding knowledge, but what's the end goal of that is knowledge about our world. How does the world work? How is what it is? Why is it what it is? We're not concerned about what we want it to be. We are concerned about what it is and why it is that. And that's a big difference between the scientist and the activist. The activist is always concerned about what will be. The scientist is concerned about what it is and why it is that way. In a lot of ways. So in social sciences and in education, such grand theories are rare, to be sure. Generalized theoretical understanding is still a goal. That's true. Sometimes it's rare to get to something completely generalized. That's a very fair statement when it comes to a theory here. And yeah, for some disciplines, that's very, very rare to get to. However, some research in the social sciences seeks to achieve deep understanding of particular events or circumstances rather than theoretical understanding that will generalize across situations or events. Between these extremes lies the bulk of social science theory or models, where what Merton called, and this is a box, this is not a thing here, what Merton called mid-range theories that attempt to account for some aspect of the social world. Examples of such mid-range theories or explanatory models can be found in the physical and social sciences. So yeah, representation of the world here was what we were after with theory, essentially. These theories are representations or abstractions of some aspect of reality that can only be approximated by such models. Molecules, fields, or black holes are classic explanatory models in physics. The genetic code and the contractile filament model of muscle are two in biology. Similarly, culture, socioeconomic status, and poverty are classical models in anthropology, sociology, and political science. In program evaluation, program developers have ideas about the mechanism by which inputs affect targeted outcomes. Evaluations translate and test these ideas through a program theory that guides the work. So what we're talking about here is, general sort of models of things. We have a understanding of how the climate works. Is another good example of this when you're talking about climate science. We have a model of how the climate works in there, and those often go in guiding climate models ourselves, and based upon 100 and some odd years, 100 and almost closing in actually on 200 years of work when it comes to climate science. It's actually an older discipline than it's given credit for most of the time, but basically we're looking for something. Theory is representation or abstract of some aspect of reality that you ultimately approximate with a model. We have very good theories about how the climate works. We have models that help to approximate that alongside of our observations and what have you. Theories enter into the research project in two important ways. First, scientific research may be guided by a conceptual framework, model, or theory that suggests the possible questions to ask or answers to the questions posed. So this goes back actually to the first principle. The first principle was about picking a question that is significant but can also be tested empirically, which means using evidence, observations, data, analysis, and what have you. You're not asking a moralizing question here. And so where this relates back to it, because one of the ways you can end up picking a significant question is in the idea of testing a theory that is out there in a different way. Or does it hold up in this circumstance or that circumstance? And this is actually what he goes on to say here. The process of posing significant questions typically occurs before a study is conducted. It's true. Usually we're asking the questions before we even do the study. Researchers seek to test whether a theory holds up under certain circumstances. Here, the link between question and theory is straightforward. For example, Putnam based his work on theoretical conception of institutional performance that related civic engagement and modernization. So that's the one thing, is that you can very much pose a question, have it be connected to a theory. You're testing some other theory, or you're using a theory to guide that question. Those are interrelated things, but it has to be related to some kind of theory of something. Another thing is, you're testing that theory. You could have a way to challenge that theory. That would be a significant question to ask, but you're challenging the theory. You are not necessarily using the theory to guide the question there. That's another way to do it. You can do that. Those are a little bit more rare to run across, I think, but you're testing a theory, so it counts as relating your research question to the theory that you're interested in. A research question can also devolve from a practical problem. In this case, addressing a complex problem like the relationship between class size and student achievement may require several theories. Different theories may give conflicting predictions about the problem's solution, or various theories might have to be reconciled to address the problem. Indeed, the findings from the Tennessee Class Size Reduction Study, Box 3.3, have led to several efforts to devise theoretical understandings of how class size reduction may lead to better student achievement. Scientists are developing models to understand the difference in classroom behavior between large and small classes that ultimately explain and predict changes in achievement. So this is different, and it's much more complicated, but it is still very much related to the second principle. What they're talking about here is, if you're asking a question that's based upon a real world problem, in my field it might be like how the climate would affect hydrology, or somebody may come to me wanting to do a study of this river is really important to my city for water resources and what have you. So they may come to me and say, I want to study that, but I, as the climate side of things, can only provide the climate side of the theory, which would be, in this case, we know the climate is changing, the increase in greenhouse gases and all of that, so I can make some estimations on what that would mean for precipitation and temperature and drought conditions and extreme rain that would affect the river. But beyond that, there's the human component, which is societal development, and how those two things interact around the river. That's an example where you would have very complex competing theories that might have to be reconciled. And it's like, how do we have a human interaction together with the climate change and with ecosystems and things like that. So a lot of interdisciplinary research is connected to practical problems and often touches on multiple theories at the same time. But there is relevant theory connected in all of those, and those are very complex studies when they're done. Very difficult, complex studies to do. So some of the most interesting research I find in my field is some of the interdisciplinary stuff where you get into the very complex things like this, where there's the many, many theories that are involved. A more subtle way that theoretical understanding factors into the research process derives from the fact that all scientific observations are theory-laden. That is, the choice of what to observe and how to observe it is driven by an organizing concept, explicit or tacit, of the problem or topic. Thus, theory drives the research question, the use of methods, and the interpretation of the results. That is true. Also, a good example of this that you might think of is that with observations of weather, for instance, and climate, we're obviously trying very hard to have our observations of the world be completely natural, which means, for example, it's not a good thing to work with a weather station that's right behind a pizza joint or right in the middle of an urban center, because that's exposed to a lot of urban development over the years. And if it's a long record station, the problem with that is you hit a point where the urban part of it and the local effect is what's really driving the temperature trend in that long-term record. So that's an interesting part of the challenge that we have right there, is that if you're really interested in measuring the theory with the urban heat island, that's the kind of station you would want to look at. But if you're really interested in just overall climate signal and you just want to look long term, you can still use that station, but you'd have to do some more analysis and what have you to account for the fact that the urban heat island grew up around there. And so so that's not necessarily representative and just entirely of the global change signal and the effect on that station. Tearing apart those kinds of things are actually a tricky challenge. So yeah, based upon the theory itself that you're really interested in, that can drive the choice of question too. So that's the fun interaction. Some people with the theory, we want to know, does this, because XYZ theory doesn't mean this for this group in the real world. That's the kind of thing. And interpretation, based upon the theory, it should do this. And if it does do this, that confirms said theory there. So that's the second principle. That's actually fairly short compared to the last video. So we had our first principle, picking a significant question that is you can investigate empirically. The second principle is relating whatever research you're doing in some way. It doesn't have to be explicit that I'm testing this particular theory to, but you're relating your research to this theory, to multiple theories, and many possible ways to do that. So that's the second principle. If you like this video, subscribe to this channel. Comment below if you found this interesting. I'm going to be releasing more soon to finish out this series on the guiding principles of scientific inquiry. Number 3 is coming up soon.